Microprocessors. They have become indispensable in our modern world and can only be produced in clean rooms under the most stringent of conditions. Sand is the basis for most microprocessors, which has a high silicon content, but also contains other elements such as oxygen and calcium. Through heating and other processes, silicon is extracted from sand and cast into blocks. Such a block has a high level of purity and is called ingot. The block is cut into wafers of the desired thickness of anywhere from 0.5 to 1.5 millimeters, depending on their intended use. The wafer is then polished and subject to rigorous inspection. If the wafer passes the subsequent inspection, the first step of production begins, which is called front end of line. Here, the integration of transistors takes place. In the first step, a layer of silicon dioxide is laid down on top of the wafer, upon which a layer of silicon nitride is applied. Then, a very thin coating of photoresist is applied. A spin coating technique is typically used to spread the photoresist over the surface. In the next step, a prefabricated stencil composed of transparent glass and opaque chrome is projected onto a lens. The lens reduces the size of the stencil pattern. The photoresist becomes soluble wherever it is exposed to UV light. The dark areas here indicate the regions that are to be removed. These can be removed through the application of an appropriate solvent. Let's look at the surface a little bit closer now. The solvent uncovers part of the silicon nitride layer which lies beneath the photoresist. The application of corrosive liquids etch away the desired regions of the other layers in order to expose the silicon. Finally, the cleaning of the photoresist and a further chemical etching of the silicon regions. Another layer of silicon dioxide is then applied, which will serve as insulation between the transistors. Etching and grinding processes expose the silicon underneath. Photolithography is used once again in the process of doping the silicon regions for the purpose of protecting the regions which are not to be doped. The silicon regions are treated with either N or P-type doping through ion implantation. This example is one of an N-type doping. The photoresist can finally be removed. Looking at the doped regions, it can be seen that the implanted electrons are able to move freely, and thus are able to carry electrical current. Finally, the creation of the gate dielectric, in which photoresist will be used to make source and drain areas through the implantation of foreign atoms. This is the fundamental structure of transistors. At this point, the front end of line is completed. From here, the back end of line begins. The back end of line begins with the application of undoped silicate glass in which holes for connection purposes are created. These will then be filled with tungsten, and the electrical connections between the transistors will be created. The end result is a wafer full of chips, which will be separated from each other using a saw and then embedded in a housing. Through the process of bonding, the chip is attached to the contacts within the housing. A housing cover serves as protection from external elements such as dust. The processes shown in this animation are greatly simplified. The production of a microprocessor can require more than 100 individual process steps and can last for many weeks. Today, a simple microprocessor can contain several billion transistors.